let's get started. So we are doing chapter 5 today. Do you have any questions about homework or last lecture? And the quiz solutions have been uploaded yesterday, so you can see all the past quiz solutions. So it may be helpful to do homework. The last quiz, it's still due tonight, so the solutions will be available on Friday at noon. Yeah, okay, so we start. So chapter 5. So chapter 5 is cross-validation and the Bootstrap. So have you heard of cross-validation before? Anyone? No? How many of you have heard of the cross-validation before?
I have.
Oh, you have? Okay.
Yeah,
in which course?
50-30.
50-30, we discussed it? Okay.
You just briefly went over it.
Okay, yeah, maybe you heard of it, yes. And maybe in some other courses, or if you come from computer science department or something, then maybe you have heard of cross-validation before. Yeah. So basically this chapter is not a statistics contents, but basically more like the simulation methods to validate statistical methods. So chapter 5 is the resampling methods. So resampling means we sample from existing sample. So suppose we have the 100 people. For example, we want to know the average height of Wayne State University students, and that we make a sample of 100 randomly chosen students. Then we calculate the average height. Maybe that is 100. Maybe male and female, but suppose the female students, maybe the average height 161 centimeter, for example, based on 100 observations. But sometimes we want to know how reliable this estimate is. But since we only have one sample, we cannot see how reliable it is. So in such a case, maybe we can sample from these 100 observations. Maybe we pick up 80 observations out. Maybe I would pick up the 50 observations from these 100 people randomly. Then we calculate the average, such as 160, the 2.1, and we pick up another 50 observations randomly from this 100. Then average height may be 160.8, or another 50. Maybe we get 159.7, and so on. Then if we see these numbers, we can see variability. So we can see how reliable our estimate is. So originally, we only have this one number, 161. That may be the best estimate, but we don't know how reliable it is. But if we resample observations, then we can see how much variability it has. Of course, the 50 observations and 100 observations are different. So maybe these estimates are a little less reliable than this estimate itself, but at least we can see some variability. And the variability is important in statistics, for example, to see the significance, statistical significance. So this is the basic idea of resampling methods. Yeah, the resampling methods is a statistical method to sample from the existing data set. So it is useful to evaluate the variability of data and the variability of estimated statistical models. For example, sometimes we estimate the regression line and we want to know how reliable that the slope is. So the cross-validation and Bootstrap are useful for that. So we have two contents, cross-validation and Bootstrap. The cross-validation may be new to most students. Maybe I mentioned a little bit in Stat 5030, but otherwise you haven't heard of it. Maybe you have taken other statistics courses. Maybe we have discussed it like 6840. Maybe we discussed cross-validation. I don't remember exactly. And cross-validation is a method to evaluate test errors with multiple randomized training and test sets. So if we have only one training set and one test set, we only have one test error. So we don't know how reliable that test error is. But if we resample it, then we can have multiple test errors, right? So multiple sets of test errors. So we can see how reliable it is. And the second one is Bootstrap. Maybe it was covered in, at least it was covered in Stat 5030. And also when I teach 5800, also we cover the Bootstrap. Have you heard of it? Maybe some of you have taken 5800, right? Have you studied Bootstrap in the course? Anyone? I think some of you have taken 5800. How many of you have taken 5800?
I'm taking it this semester.
Oh, okay. So still maybe in chapter 7 or something. So maybe
I took it. I just don't. It was a few years ago. So I don't remember.
Okay, I see. Yeah, so Bootstrap is an important method, and the Bootstrap is the method to estimate distribution of parameter estimates with multiple sampling from the data set. So for example, when we have regression model such as y is equal to 1.2 plus 2x plus epsilon, suppose that these are estimated numbers, then in regression analysis that we calculate these based on IID normal assumption of errors. So if we have such many assumptions, then we can calculate standard error theoretically, and then we have the standard error such as, okay, so we have the standard error of 0.8 for this slope. So we can calculate the T statistic based on this, and we can calculate p-value, but that can be done with many assumptions. But sometimes the situation is more complicated. Observations are not IID, and maybe some individual have multiple measurements and so on. So in such a case that we cannot really calculate the standard error theoretically, so that we have to use the more numerical methods to evaluate the distribution of parameter estimates, like this slope. So that is the Bootstrap method. Okay. So cross-validation is a better way to evaluate test error. Bootstrap is the more general way to estimate the distribution of parameter estimates. And we deal with cross-validation, CV, in 5.1 and Bootstrap in 5.2. Probably we can finish both today. Okay, so just a review of validation set approach. So the simplest method to evaluate the prediction performance is the validation set approach. So remember that the data set is divided into training set and the test set. And estimate statistical model with the training set. So suppose we are estimating the slope of regression line, then we have x value and y value. X is 1.1, y is 3.2, x is 0.7, and y is 2.5, and so on. And maybe the 5.0 and maybe 14.9, something. Then we can estimate the regression model. So y is equal to maybe 3x minus the 0.1, and these are estimates. Then we evaluate the error size with the test set. So this is the training set, and this is the test set. So if we observe the some numbers, then we can use these estimates, 3 or 0.1, negative 0.1, to calculate error size. For example, the first observation, you can calculate error size by y minus 3x plus 0.1. So, okay, so the error size for the first one is equal to maybe y value 3.3 minus 3 times 0.9 minus 0.1. So 2.7, 2.6. So this is 0.7 and so on. So we can evaluate the error. So the important thing is from the training set, we estimate parameters. Then with the test set, we calculate error. And there is a trade-off between accuracy of statistical model and the accuracy of test error. So the estimated model is more accurate when training set is large. Of course, we have a larger training set, then we have more information to estimate parameters, so more accurate model. But the test error is less accurate since the remaining test error is small. So think about the situation that we have 300 observations, and so training set that we have 295 observations and the test set 5 observations. Then the model is reasonably accurate because the training set is large, but the test error is based on just these 5 observations. For example, we have some outliers exist in a test set. Largely, the test error is evaluated by just that outlier. So really, the model itself doesn't matter, and this is also just a gamble. So if the model can fit well for that outlier, then the model performs better. So it's really the large test error. Large error to evaluate the test error. So the accuracy of test error have a problem. But if the training set is only 5 observations and the test set is 295 observations, then of course we cannot train the complicated model with 5 observations. If we fit, for example, cubic curve with this, we have 4 parameters, then we have only 5 observations. So it's almost nonsense, even though test set is large enough to evaluate test error. So we have a trade-off between these two. So we want to solve this trade-off. We want to have a larger training set, but we don't want to have a smaller test set. So we have to, we have to solve this trade-off problem. I think that before that, we have one more slide. So the data set is divided into training set and the test set randomly. And okay, so that should be training sets and test set are determined randomly, because if we pick specific observation as training set, we may have some bias. So we have to do it randomly. But if we do it randomly, we have some randomness in test error. So this is the test error size, mean square error, so test error size. And this really depends on how to divide the data. If we are lucky, for example, all outliers are in a training set, but it doesn't affect the model because it doesn't have a large leverage or something, then test error should be very small. We estimated a good model, and the test errors are all good observations. But if we are unlucky, that we just by chance chose the specific type of observations in training set. And if test sets are totally different, then of course we have very large test error. So depending on the selection of training set and the test set, we can have the large, different size of test error. So the y-axis is test error, and it really depends on the the choice of training set. So the left-hand side, we just do validation approach once. So right-hand side, the figure shows the test error for 10 data set, 10 different training and test data sets. Even though the original data sets are the same, the division of training set and test set makes different size of errors. And you can see that the, okay, so these graphs have different levels, right? So this, for example, yellow one, we are very lucky to divide training and test sets. Training set and the test set are really similar in characteristics, and the test set have fewer outliers. So the test errors are almost always smaller than other cases. On the other hand, maybe this one is really unlucky case. So training set and test set may have different characteristics. So error is always larger. And here we fit several different models. So probably they fit the polynomial regression. Yeah, so we regress the MPG on horsepower in a car dataset, auto dataset. And so this x-axis is the model complexity, so the degree of polynomial. So degree of polynomial 1, so we fit the model y is equal to beta naught plus beta 1x, but the model degree 4, we fit the y is equal to beta naught plus beta 1x plus beta 2x square up to beta 4x to the fourth power. So model is more complex, then sometimes model performs better, but sometimes model performs worse. Overall, probably the error size is smaller, maybe around 3 to 7. And after that, the error size gets slightly larger. As a tendency of all of these, the training and the test sets, probably the tendency is like this. So probably 3 to 7, the degree of polynomial is 3 to 7, maybe the the test error is smallest. So training and test set, basically it's better to try several times. We randomly divide the data set and the result depends on the randomness. So we want to eliminate that randomness. So if we try training and test, the validation set approach several times and take average, then our result should be more stable and more reliable. And the first one, so to solve the trade-off problem in the validation and the test approach, the training and the test set approach, the one best way is the leave one out cross validation. So we have n observations. Suppose that we have n observations in the original data set. Then we divide this into 2 data sets with training data sets with size n-1 and test data set with 1 observation. So training n-1 observations and the test set the 1 observation. So training set is large, so training set is good. And the test set, we only have 1 observation, so we have a problem. But we try this n times. So first try, we choose just first observation as the test set, but the remaining observations as the training set. And we evaluate test error. I would say maybe ERR1. Then next, we try second observation as the test set, and the remaining n-1 observation as the training set. Then we can estimate the model, then calculate the test error. Say this is the error 2. And we repeat this for all n observations. So we repeat n times. If we have 1,000 observations, we have to repeat to fit the model 1,000 times. So it is basically 1,000 times more time consuming than usual training and test approach. So this is error 1,000. Then if we take the average of these errors, then still that we evaluate the test error for each observation once. So the result is pretty stable. So we have large training set, and effectively we have very large test set also. So this is much better than cross-validation. The drawback is we have to spend 1,000 times more time compared to simple training test approach. But this is much better. And now computer is very fast. So if you program everything, it's not a problem to estimate it. So this is the one leave one out cross-validation approach. So we leave one out. So leave one out as the test set. Yeah, so to summarize, the procedure is this. So suppose x1, y1 to xn, yn are observations. Possibly that these are multivariate. For example, x1 maybe x11 to x1p. So possibly the more than one numbers. And suppose these are observations. Then the LOOCV, leave one out cross-validation, that splits the data set into training set with n-1 observations and the test set with 1 observation. And suppose that the XIYI is the test set, then we estimate the model with training set, and the yi hat is the predicted value for yi. Then we calculate the test error, yi minus yi hat, and say this as MSEI. I wrote error 1, error sub I in the last slide. And then we repeat this basically n times for all possible i's. Then calculate, sorry, I think I have some error. So we calculate the error for everything and we take summation. So Cn n is the I is equal to 1 to n MSEI, then take average. So this is the cross-validated error. I think I have to fix this slide. Also, this is n. Okay. Yeah, so in this way, the training set is large so that the estimated model is as accurate as the estimated model with all observations. And that is the bias of the CV error against the true test error is very small. Oh, here the bias means that the usually the validation set approach, with the validation set approach, the error is overestimated. Because suppose we have 100 observations and we divide this into 70 observations for training and 30 observations for test, then training set is smaller than our entire sample. So that means that we have less information. So that should be less accurate. So usual test, validation set approach overestimates the error size a little bit. So, but the in this case, we use 99 observations as a training set. So the bias is very small. And the training set is large, so the model has, and also the training set is large, so the model has less identification problems. So maybe this is very practical issue, so we can introduce this one. Suppose that our model, for example, suppose we have maybe just the 2 predictors and 1 response variable, and the 10 observations. Just this is for illustrative purpose, so just a small data set, and okay. x1, x2, and y. And if x2 is very sparse variable, then we have trouble in training the validation set approach. The sparse means, for example, the x2 is indicator variable and only two ones and 8 zeros. And x1 maybe the categorical variable, no, numeric variable such as this. And y is maybe the response variable, maybe also continuous scale, 120, 135, 201 or something like that. Then if we apply the validation set approach, we have trouble for x2 sometimes. Suppose the validation approach, the training set with size n1 is equal to 7 and the test set n2 is equal to 3. But the training set is, suppose that these observations 1, 2, 3, 4, 5, 6, 7. Then we only have zeros in training set. So that means we cannot specify, for example, coefficient of x2 when we do linear regression. We need really 0 and 1 in training set. So at least the one observation of these. Right. So we have trouble to estimate the model such as y is equal to beta naught plus beta 1x1 plus beta 2x2 plus epsilon, because this one is not estimable. With the training set. If only 10 observations, you can see at once. But if you deal with many variables, if we see many variables, maybe hundreds of variables, and we have like 500 observations, always we have this kind of problem. So larger training set is really necessary to estimate parameters. Even if the x2 is not this sparse, for example, we have 500 observations and we have maybe 20 ones and 480 zeros. It's a kind of reasonable, right? It's a kind of reasonable, but if we try training and test set approach for something, I mean, maybe the cross validation, yeah, so we set the training and the test approach. And okay, so we have maybe 100 variables of this property. Then even if each variable have 20 ones, still, if we randomly just pick some observations, maybe for some variables we have identification problem. For example, we ask, I don't know, so we ask Wayne State University students whether they took the stat 5800 or 5820 or mass 5800 or something like that. Then each class is very small, so only 20 students answered yes. But if we want to estimate parameter for those classes in some regression model with Wayne State University students, then we have trouble if only one variable, even one variable has this situation. So to avoid this situation, really a large training set is, desirable. Yeah, of course, if only one observation has 1 and the others are 0, still the one leave one out cross validation has trouble. But that variable is problematic originally if only one observation has value 1 and the others have zeros. Yeah. Yes, so that is explained here. And also a good thing about leave one out cross-validation is that there is no randomization in the methods. So in the first, in the beginning of the class, I mentioned that when we have 100 observations of students' height, we can randomly pick up 50 to see the variability between the observations. But the randomly pick up 50 observations, that has some randomness. So it really depends on your computer, depends on the random numbers you generated in your computer. But here, the method is very, deterministic, right? So this procedure is the same when I run or when you run. So it doesn't really depend on any randomness. So it's a positive side of this method. And the typical, the most obvious downside is the computational burden is large. So if there are 100 observations, you have to estimate the model 1,000 times. Any questions so far? Okay, and here, yeah, go ahead.
Well, so I guess for leave out one, could you do it with more than just leaving out? Well, I guess that counts. No, I don't know.
Sorry, leaving out?
So it says leave one out.
Yeah.
I guess, can you do it where you leave more than one out, or does that?
Yes, that I will discuss in the next section.
Okay,
yes.
okay.
Yeah.
All right.
Yeah. And the leave one out cross-validation. Yeah, that's a good question. So leave one out cross-validation is time consuming, but for specific models, actually there are some shortcuts. So if you fit a linear model, then you can actually do cross-validation, leave one out cross-validation very simply. So actually the leave one cross-validation is calculated by this. So yi hat is just the estimate with all observations. Based on the model with all observations. So we only estimate once, then we can calculate the cross-validated errors. And we have the yi minus yi hat square. That is the usual, the error size. But we divide this by 1 minus hi. So yi minus yi hat over 1 minus hi. Then take square. Then take average over I. Here, hi is leverage statistic. For ice observations. So leverage statistic appear here. So if leverage statistic is 0.5, that is very large value. In such a case that we have 1 minus 0.5 square, the 1 over 1 minus 0.5 square. So actually this observation, ice observation have the 4 times more impact than observation with hi is equal to 0. Actually, the hi is between 1 over n and 1, so it cannot be 0, but it's very close to 0 if n is large. Hi is on average p over n, where p is the number of parameters. Yeah, then the computational burden is just the same order as fitting a linear regression. So we have to divide this by hi, but it doesn't really matter. So we have to estimate model once. And hi, we have to calculate hi for each i, but that is everything. And everything else is easy to calculate. So for linear model, ROOCV is really a good option. Any questions so far? So now, yeah, you can see the meaning of leverage here. So leverage is large. That means that observation has too much impact on the estimated errors. The cross-validated error. But usually the hi is pretty small number. if that is okay. So n is suppose 10,000 and the many of hi is 0.0002 or something, and sum of hi is 0.1, and that doesn't really matter much. Of course, if hi approaches to 1, that's problematic. That's problematic. Okay, so next, the k-fold cross-validation. So suppose the model takes a lot of time to estimate. For example, even logistic regression, it takes much more time to estimate compared to linear regression. And more, like neural network or support vector machine, it takes more time. So it's not realistic to run 10,000 times, even if we have 10,000 observations. So now that we think about k-fold cross-validation. So here, this figure explains with the k is equal to 5. So basically, that we randomly split the original data set. This is the original data set into 5 pieces. Maybe the data 1, data 2, data 3, data 4. Sorry, data 3, data 4, data 5. Then just the one group as test set and the remaining group as training set. So training set should be large. So each time we use 80% of observations as training set and the 1/5 as test set. Okay, so 80% is worse than n-1 over n, but still much better than like 50% training and 50% test. Okay. And also, all observations are used once, right? So the D1 is test set in this simulation, and the D2 is test set, and the D3 is test set, D4 is test set, and the D5 is test set here. So we run only 5 times, but still we can use 80% of observations each time as the training set, and each observation is used just once for the test set. So that's good to, suppress the variability in the result. So it looks good. We have to run only 5 times. Even if you take 1 minute to run a model, the waiting for 5 minutes to get much more reliable information is not bad. So 5-fold cross-validation you can use.
I have a question.
Sure.
Maybe you addressed this already and I missed it or something. So when you do it this way, you get five different models, right?
Yeah, 5 estimates. Yeah.
Yeah. So how do you determine which one's the best one?
So we take average of these errors.
Okay.
So the objective is to estimate the error size correctly. So in the first run, we estimate the test error based on these observations. So we get the error MSE1. And this from second trial, we get MSE2 and MSE3, 4, 5. Then we take average to get more reliable estimate for MSE.
So you don't pick one model, you take the average of the models?
Oh, I mean, the model is the same, we have the observations. So model is like the same model, beta naught plus beta 1x plus beta 2x square plus epsilon. And we estimate this model with this 80% of observations for the first run. And the second simulation, that we estimate the same model with different training set, D1 plus D3 plus D4 plus D5. So since data are different, estimates are different. Yeah.
Okay, so beta 1, 2, 0, 1, and 2 are all the same for all 5. Okay.
Yeah, so the model itself is the same. Yeah.
Okay.
Estimated numbers are slightly different. Yep.
Okay. All right. Cool. Thank you.
Yeah, so we have, the much more complicated situation, right? So finally, of course, we want to compare different models, but we are talking about how to, calculate MSE more, accurately with a specific model right now. Okay, so the k-fold cross-validation. the method is to divide the data into k equal groups randomly and use the ith group as the test set and the remaining k-1 groups as the training set, and to evaluate MSE, say MSE sub I, and repeat this for all possible i's. In the previous slide, the I is equal to 1 to 5. Then calculate the cross-validated error as the average. Yeah, so to compare different models, we have to do this for each model. Then we get the cross-validation, k-fold cross-validation error with, the model 1 and the model 2 and the model 3. So then we can compare cross-validated errors. Maybe this is a good illustration. So example 1. So, okay, so true curve is the black one. So black one is the truth. Okay, black is truth. Okay. And these observations are simulated data points based on the black curve plus some error. So like this. So error is distributed normal. Right? So we can make this simulation data set. Okay, then we can estimate the model. We tried actually the 3 different models. So this is the straight line. We just fit the straight line on the model. And the second one is the blue one. The blue one. So this is okay. So this is the y is equal to the beta naught plus beta 1x. And the blue one is the y is equal to the quadratic equation. So beta naught to beta 4x to the 4th power. And the green one is actually the 20 polynomial with 20 degree. So green one. So this is the y is equal to beta naught plus up to beta 20 x 20. And we want to see which is the most accurate based on the cross-validated k-fold cross-validation error. So what do you think? Which is the most accurate? The blue curve or green curve or this yellow line? So in this simulation, so which one is most accurate? Anyone? The blue or green or yellow?
Is it the blue?
Yeah, blue one is the most accurate, right? You can see, we know the truth. We know the truth. Truth is black. And you can see that the blue line, blue curve is closest to the black one. Green one is overfitted to the data. So it's disturbed by error. For example, see these observations. So green one just accurately capture these data sets, but this is just because of the error size. And the true curve is here. Right? And the yellow one is too simple. Maybe overall tendency is correct, but the at least for example, so this part should be better if it looks like this. So it's not really optimal. So the blue one is the best. Okay. If we use the training error, which is the best? Blue, green, or yellow? Just use the training error, distance between graph and the. You can see the green one is the best in terms of training error, right? So because they just overfit the situation. So always the observations are closest. Not always, but most of the time, observation is closest. So the situation is explained by this. This is the cross-validated error. And this is the training error. Sorry. I mean, the training, training set is 100%. So training error. Training error is always smaller if model is more complicated. So green one has smaller error size. So this is MSE. So training MSE is smaller for more complicated model. But the cross-validated error, it's not appeared in this figure, but the cross-validated error is calculated. Then actually the blue one has the smallest error. So cross-validation can be used to find the best model. Validation and test approaches, validation set approach is good, but it has more, variability. Cross-validation, more reliable estimate. Also, the size of error, the cross-validated error is similar to the true error size if we utilize all the data set, all of the data set. Example 2, it's similar. Black one is the truth, and the yellow one, green one, and the blue ones are estimated model. And you can see that in this case, which is the best? It's really hard to see. Yellow one and the blue one are almost equally good. Green one is the worst. Okay, so the yellow and the blue lines, curves are similar to the black one. Probably black one is complicated curve, but it's very smooth. So even straight line can capture it well. And the training error, always smaller for more complicated model. But the test error, you can see that almost the straight line, that means the two parameters, or I think this is just the quadratic curve. Blue one is quadratic curve, and this is almost the same. And the green one, much worse. Yeah. So cross-validated error is almost always worse than the training error because we don't know the true answer. But the size of getting worse is different depending on the model. More complicated model, the test error, cross-validated error is much worse than training error. Simpler model, it's very similar. Do you think is the cross-validated error can be possibly better than training error? What do you think? Like more students with good sense of numbers? Anyone think that the cross-validated error is possibly better than training error? Just for a specific case. Anyone? Some bonus credits for this? Answer is actually yes, it's possible. So suppose that we have 10 observations. Maybe just the height of students, 159, 160, 162, 161, and maybe 160 again. And the other 5 observations, 180, 179, 175, 172, 178, something. And sorry, it may be difficult to estimate. So suppose that the error size, sorry, it may be difficult to see it. Sorry, I think it's a little bit difficult to construct an example, but basically data can be can generate any results. So the cross-validation error is usually larger than training error, but we cannot absolutely say that cross-validation is always larger error than test error. And example 3, it's similar. So black one is the truth, and the green one, blue one, and the yellow ones are estimated. Then certainly the yellow one is the worst, right? So in terms of training error, it's worst, but also the cross-validated error, also the worst. And actually, that blue one and the green one are similar. So black one looks the cubic curve, but actually probably I don't know, a little more complicated one. And the yeah, the blue one is slightly better than the green one. So blue one is the best model. So the polynomial with degree 9 probably is the best to fit the model. And maybe another practical question is this cross-validated error always smooth curve or not? And actually, this isn't really smooth all the time. Often we observe the cross-validated error is like this. Maybe it's not clear what I want to say. Sometimes we see this kind of graph. So you can see that this true curve, black one, goes to infinity as x goes to 0, or x goes to negative infinity, and goes to negative infinity as x goes to infinity. So that means probably the polynomial with the highest degree equal to an odd number is good. Maybe first degree, third degree, the 9th degree, those are good. If we fit, for example, the parabola on this, then probably it performs worse than straight line. So in such a case, maybe cross-validated error is like this. So always smaller when, degree is odd number, and the degree is even number, slightly higher error. So that is also possible. So this is the cross-validation. Any questions? And in real data analysis, the situation is less clear because we don't know the true curve. So this black curve is available because this is a simulation. Okay, so next one, the bias variance trade-off of k-fold cross-validation. Yeah. Okay, so in this figure, the blue curve is the true error rate. So true error rate can be calculated if everything is known, such as simulation. So we know the error size. So true error size is this one. And the black dashed line is the LOOCV error, and the orange curve is tenfold cross-validation. So LOOCV is the CVN, so N is large, and cross-validation 10, CV 10, so we only have 10. And yeah, the truth is blue, and the yeah. So LOOCV and the tenfold cross-validations are similar. And it's sometimes different from truth. Sometimes it underestimates the parameter. Why? Underestimates the parameter. Yeah, not clear. Actually, this is underestimated, but this and this fits well, and it really depends on the data. So sometimes it's not that accurate. Yeah, it's really hard to see. Yeah. But at least we can say that the LOOCV and the cross-validation with the, tenfold are similar in results. So the LOOCV is basically cross-validation with k is equal to n. So people often use k is equal to 5 and 10, 5 or 10. So yeah, so basically not important. The choice of k is not important. In statistics, some parameters are more important and some parameters are less important. So if you have studied the Bayesian statistics, we have the so-called prior distribution that is basically less important than final estimated parameters. So usually we have some default value. So many of the R packages have the default k is equal to 10. Maybe 5 to 10 are typical numbers. If model is very computer intensive, I use sometimes k is equal to 3. That is 3 times faster than k is equal to 10. And the large k gives a smaller bias to estimate the test error. So yeah, so remember that hopefully we have the same size of training set as original data set. But to do that, we have to take all observations as training set. So if n is equal to 100, then the best thing we can do is the training set with sample size 99. Right? N1 is training set size, then at maximum 99. And that is the LOOCV. So bias is smaller. If N1 is only 75, basically we have overestimated the error. Large K, more computational time. And the last one is a little confusing, but the large K has a larger variance to estimate the test error. It's not intuitive. Anyway, we do cross-validation. So each observation is used once, as a test set. Okay, so it sounds the same variability, but actually the textbook claims that the large K has a larger variance to estimate the test error. Yeah. So we estimate the test error n times if LOOCV. But in that case, the training sets have excessive similarities, right? So if we have 100 observations, first training set this first training set includes the first observations to 99th observation, and the second training set includes the first observation and the third observation and up to 99th observations. And these training sets are really similar. So estimated models are too similar, the textbook claims. So that's why sometimes we have a problem that the variance to estimate the test error is too large. Yeah, I think that this is a little minor issue, but still it's important, the textbook mentioned. So it's almost art. It's really hard to interpret mathematically. Yeah, so that's the cross-validation. Do you have any questions so far? So usually the larger K is desirable. Yeah, and practically maybe K is equal to 10. Yeah, to get more reliable estimate, sometimes we can do tenfold cross-validation several times. Yeah, that may be useful in this context if we have an optimal case. Suppose optimal case 10. Then we do training and a test, validation set approach 10 times in, tenfold cross validation. But if that has some randomness, we can try k-fold cross validation several times. Yeah, so that can be possible. Yeah. And cross validation is also used for classification. But in the cross validation, usually we use the mean square error as a measure. But for classification, we don't have MSE. MSE is basically the squared distance, right? Squared distance. But in classification problem, we have, basically the more discrete decision making. So we only have the 3 classes such as ABC. So we cannot use MSE. So then we can use the error size to estimate it. We do some testing and we do some estimation and we do classification. And we get this table. Then these are correct classification and the others are wrong classification. So the error rate is equal to 1, 1, 1, 2, 1. So 5, the 5 over 17. Okay, so we can use this one instead of MSE to do cross validation for classification problems. But that is less reliable maybe because the numeric variable has much more information than categorical variable. So think about maybe just to use computer to use make the number, right? So then basically we use maybe like the 16 digits of binary numbers to make one continuous number in computer, right? So that means the one number, the 16-bit number has the 16 times more information than binary variable. So that means that this kind of methods can work only for very large data set for classification problems. Continuous response, more information. So maybe relatively smaller sample may make sense for cross validation. But the classification, basically, we have a larger, we need larger sample size. Yeah, so this is a pretty simple idea, but also it has some problem. So error rate. Error rate is optimal. Usually classification problem uses different strategy to estimate the model. Logistic regression use the likelihood function to estimate the model. It's not error rate, right? Likelihood function is more continuous number, so it may have more information if the structure is identified correctly. So logistic regression uses uses likelihood function to estimate the model. But if we evaluate that model by error size, then it may be problematic. Yeah. Yeah, it's possible that the best logistic regression have error rate of 51%. So binary classification problem. So if we optimized, that accuracy should be higher than 50%, right? But sometimes less than 50% because we use the likelihood as the method of estimation. And also LDA, QDA, KNN, all of those. Maybe KNN is maybe fine, but the LDA and the QDA also have different mechanism to estimate the model. So not necessarily that it's optimized for minimizing error rate. Yeah, so, but if we have enough number of observations, for example, that we can use the cross-validation to look for the best model, best logistic regression model. For example, the best logistic regression model among these. So suppose the probability of success is based on the polynomial of x1 and x2, and we want to optimize this k, then we can calculate the cross-validation for optimizing the degree of polynomial. And actually, this is the that example. K is equal to 1, 2, 3, 4, and the true base decision boundaries are estimated by logistic regression. And the usual logistic regression, the only linear term, this decision boundary is linear, but the quadratic and the cubic and the quartic curve, then we can estimate this. And certainly the degree 3 and degree 4 look much better than the first two. So optimal K is probably the larger than 2. And this is actually the result, the training error and the test error and the tenfold cross-validated error. And the tenfold cross-validated error is black, okay? So you can see that the degree 4 is optimal. Maybe 3 and 5, maybe the next best. Yeah, do you have any questions on cross-validations? Yeah, we discussed how to code cross-validation in a lab session. It's not that difficult as long as we know how to randomly sample observations. Okay, so the next one is the Bootstrap. The Bootstrap is the method to estimate the distribution of parameter estimates with the sampling from dataset. So, you know, the image is that suppose that we estimate y is equal to beta naught plus beta 1x plus epsilon, and we want to estimate the distribution of beta 1, then we pick up, you know, we randomly sample the data set and we estimate the beta 1 many times. Then we have estimator, the distribution of beta 1 hat. This is a histogram. So frequency. If we estimate the model once, then we only find just one estimate of beta 1 hat, but if we do it many times, then we get this kind of distribution. So suppose that we have n independent observations in the sample. For example, if observations are all independent, that's fine. If not independent, we have some other ways. But and we want to estimate a parameter alpha, for example, population mean or population variance or slope of regression. At first, randomly sample n observations with replacement. So that means, for example, if we have 5 numbers here, we randomly pick up 5 numbers, but the same number can appear more than once. Or here, same number can appear more than once, actually the 3 times here. Then we can make the new data set, new kind of simulated data set. So the principle is that if we observe these 5 observations, we can interpret this as observation is 1 with 1/5 probability, observation is 2 with 1/5 probability, and so on. So this is so-called empirical distribution. So based on this empirical distribution, if we have many observations, maybe 2 can be selected more than once, 2 can appear more than once, right? And 16 appear more than once, and so on. And some observation may not appear in some specific data set. So that's why that we do the sampling with replacement. That is a good way to do simulation based on this empirical distribution. Yeah, and we can use this sample function to do that. Sample and the original set and replacement is equal to true. And the point is that the size of the data set does not change, still the 5 observations. Then calculate parameter estimate, say alpha I hat from the sample. Then repeat these steps many times, say B times. I would suggest the B is at least a few hundred. Not really needs to be very large. Maybe this is one ballpark estimate. In academic journals, maybe we can have a larger B, maybe 10,000. And make a distribution of alpha 1 to alpha B, then we get this kind of distribution of beta 1 hat. Yeah, so if you want to calculate the variance of alpha hat, that is often the case for testing. The estimate is obtained by the bootstrap as the 1 over B minus 1 summation I is equal to 1 to B alpha I minus alpha bar. Alpha bar is the average. Yeah, so just usual formula for sample variance. Any questions so far? If not, we have some examples. So suppose we have 5 observations. These 5 are, I think, the weight of newborn babies. Okay, so, and we want to calculate the mean and the standard deviation. So mean and the standard deviation, mean is here and the standard deviation is here. Mean is 4.64 and standard deviation 0.61. And now, second question, estimate the standard error of the mean theoretically. So suppose that these are IID random variables, x1, x2, x3, x4, x5, and this follows the normal, the mu sigma square, then x bar is x1 plus x2 plus up to x5 divided by 5. So if we consider the variance of this based on the IID assumption, variance of this is the 1/5 of the variance of x1 or x2. Anyway, these are the same. So sigma square over 5, right? And the sigma is estimated by sample variance. So standard error is estimated by, sorry, the standard error of x bar is equal to sigma over square root of 5. So this is estimated by sample standard deviation divided by square root of 5. So this is very, the simple problem. So we can theoretically calculate that this, the theoretical standard deviation of x bar. But this can be obtained by bootstrapping. So we repeat sampling from x with replacement. Then for each repeat that we calculate mean, then we have 100, different the sample means. Then we take the standard deviation of it, then we get a similar number to this. And this method works pretty well, especially for moderately large sample. We have only 5 observations, so still we have some bias here. But if we have 20 observations, 30 observations, almost we can ignore the bias, and just this simple simulation methods can calculate the standard error of our estimate. Yeah, so theoretically we can calculate in this way, but the bootstrap can calculate it just numerically. Yeah, so the estimate tends to be slightly smaller than answer, but still a good estimate. Bias becomes negligible when the sample size becomes large. We have only 5 observations, but if it's moderately large, it's pretty good. Even n is equal to 5, you can see the estimate is reasonable enough. And bootstrap is particularly useful when the theoretical distribution of estimate is very hard to obtain. For IID sample linear model, that's fine. But if we have more complicated model, it's much more convenient to use bootstrap. So when I worked for the medical hospital, I used bootstrap very often. It's very practical way. Yeah, so the previous example only X variable, but in general that we have this situation. We have a data set like this, and this one just a toy example with only 3 observations, but we randomly choose 3 observations with replacement like this. Then using this data, for example, that we can estimate the y is equal to beta naught plus beta 1x plus epsilon. And then we can estimate, for example, the distribution of beta 1 hat. Sorry, this is the last slide. So suppose that there are, okay, so suppose a little more complicated situation. We have the 200 observations for the response time to a signal and the alcohol content of blood. So that we are thinking about the effect of alcohol on the response time to a signal. But the data set is a little more complicated, and the same person is measured more than once. So 200 observations come from only 82 persons. This is very typical data set in biology or the medical data. And we want to estimate the y is equal to alpha plus beta x plus epsilon, but also we want to calculate the variance of alpha hat and the variance of beta hat. But the usual theory does not work because these observations are not independent. Observations within each person is highly dependent. Okay? Some very quick person can respond to the signal very quickly, even if they are drunk. So in such a case, we can use the Bootstrap by randomly sampling 82 persons, not the 200 observations. So we have to randomize based on independent observations. So 82 persons are independent. So we randomly pick up 82 persons, then estimate the regression line, and we repeat. This is entirely the simulation methods. So we can estimate the distribution of beta 1 hat, the distribution of beta or distribution of alpha. So in this way, the Bootstrap is very useful. So if you use non-IID dataset, then but the datasets are reasonably independent with some groups, then we can use this method. Yeah, so that's it for today. Sorry, I extended a few minutes. If you have questions, you can ask me. Otherwise, let's see you next week.
Thank you. Have a good night.
You too.
Thank you.
Thank you.
Thanks.